All right, another common example you might see or test question is a hydraulic lift. So a hydraulic lift uses confined fluid, um, which is not very compressible, to go ahead and transfer the energy. And so in this example here, I have 500 pounds exerted over this plate with a cross-sectional area of 20 square inches. So A1 is 20 square inches. So the nice thing about a hydraulic lift and properties of fluids is Pascal's law. So Pascal's law says that the pressure exerted on a confined fluid is transferred everywhere undiminished. So the pressure at this point here is going to be the same as the pressure at this point here, the same as the pressure at this point here, same as the pressure on this entire plate here. Okay, so because of the pressure and the fact that I increase the areas here, this increasing area pretty much means that I'm going to have an increase in F2, this output force. So the question is, if a hydraulic lift is used with the given values, could a car weighing 4,000 pounds be lifted? Okay, well, how do I calculate pressure? Well, I have 500 pounds input on this 20 square inch plate piston here, so pressure is force over area, like stress. Okay, so I have 500 pounds over 20 square inches. Notice that pounds per square inch, or PSI. So what does that give? What's 500 over 20? That should give us 25 pounds per square inch. So, because of that input force, I have 25 psi in my fluid exerted everywhere undiminished. So the pressure doesn't decrease over here, it doesn't decrease over here. It's 25 psi everywhere. Now, because of this increase in area here, now I'm going to have an increase in force. So the question is, if hydraulic lift is used, could a car weighing 4,000 pounds be lifted? Can this F2 overcome this 4,000 pound car? I'm not sure. Let's try it out. Okay, so on the output side, pressure is equal to force over area. Well, I know what my pressure is. My pressure is 25 psi. I know what the area is. The area for that piston is, so if I looked at this directly from the bottom, you would see a circle down here. That's 100 square inches. Will this produce enough of a force F2? Well, 100 times 25, 25 times 100 is what? 2,500. So 2,500 and if I'm multiplying by 100 on both sides to isolate F2. So times 100 square inches. So that's going to cancel out 100 square inches times 25 pounds per square inch. So the square inches will drop out, leaving you pounds. So 2,500 pounds is my output force, F2. Is this enough force to move a 4,000 pound car? The answer is no. So let's extend it. What would I need to do so that this could be enough force? Okay, so that this would produce enough force. What could I do to the situation? I'll let you think about it for a minute. Go ahead and press pause and think about it. All right, now that you've thought about it, the two things you could do are, one, you could increase this input force 500 pounds. So 500 pounds, if I increase that to 1,000 pounds over 20 inches, then I'd produce 50 psi. And 50 psi times 100 square inches would give me 5,000 pounds. And that would be enough to lift that 4,000 pound car. The other thing you could do is to modify your hydraulic lift to where you increase the area of the output piston. So if I increase the area of the output piston by 200 or into 200 square inches rather than 100 square inches, so double it, then I would then double my output force F2 as well, and that would be 5,000 pounds, and that would be enough to lift that 4,000 pound car. Okay, so you can see that by using hydraulics, a confined fluid, you can get huge multiplication of forces just by using different piston sizes. Have a large force over a little itty bitty area, and have that multiply big time on a larger area. So you get a huge output force. And that's how they can lift your cars. That's how these big hydraulic machinery work to lift or dig into holes. So hydraulics is actually quite nice. You can get huge multiplication of forces, nice steady movement. The drawbacks are sometimes that they're messy when you do have leaks in the system. So thanks for watching.